Welcome to APA's weekly webinar. My name is Billy Zadig, Manager of Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to APA's webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as a link to our upcoming webinars. We have webinars planned out through December 2021, and many are open for registration. Professional continuing education and AIACLU credits are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @apa.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by our presenter. At this time, it's my pleasure to turn this over to Christine Parrington, who will introduce our speaker. Christine, take it away.
Thanks, Billy. Good afternoon, everyone. Thanks for joining us today. We're excited to be presenting virtually for APA. My name is Christine Parrington, and I'm the Director of Strategic Growth here at AQUIS. I'd like to introduce to you our speaker today, our President and CEO, Mike Bedone. Mike has been with AQUIS since 2008 and is an alumnus of the College of Engineering at Rutgers University. He earned his bachelor's in mechanical engineering and began his career with GE Plastics and later served as Director of Engineering for CHEP, which is a leading international supply chain management company. In early 2004, Mike and a colleague from GE Plastics were approached and asked to develop a fire code compliance solution for the refurbishment of mechanical air handling units. Successful pioneering soon led to the formation of AQUIS, which has grown exponentially over the past 15 years, largely through Mike's leadership and vision, earning the trust, respect, and business of many of the nation's top hospitals, universities, government organizations, and Fortune 500 companies. Mike is a native of New Jersey and has lived in Orlando with his wife and 3 children since 2000. And on that note, Mike, take it away.
Thank you, Christine. Good morning and good afternoon to everybody. It's a pleasure to be presenting to you today the topic of air handling unit, coil, and tube restoration, driving improved indoor air quality and energy savings through innovation. Now, before we delve into this topic, it's important that we address or discuss the root cause of our issues here, and that is biofilms. And so what are biofilms? Well, biofilms are communities of microbes, which include bacteria, fungi, viruses, spores, that grow on surfaces and have the ability to live for extended periods of time. Now, we're all accustomed to the paradigm of microbes floating freely in the air in what's called their planktonic state. But in reality, most microbes actually live and flourish within biofilm. Now, one of the key features of a biofilm is that they're protected by what's called the EPS, which stands for the extracellular polymeric substances. The EPS is a strong, tacky biopolymer which serves to protect the biofilm. Now, thanks to the EPS, biofilms are very resilient and highly impervious to common cleaning chemicals like bleach, quaternary ammonium, and they're also very resistant to UV radiation. Biofilms are largely responsible for the proliferation and spread of pathogenic agents such as Stachybotrys, Staph, Legionella, COVID-19 as well. And it's a known fact that 90% of harmful pathogens exist in the form of biofilms. So right now I'm going to show you a short video to help explain the typical behavior of biofilms. Now, biofilms will start in a planktonic state and land on a surface where they'll quickly work to colonize that surface. The microbes will quickly multiply and join in force with other types of microbes. They will form layers in the process, and so a biofilm will be a complex structure of multiple layers of different types of microbes. Now, the way that microbes within a biofilm are known to communicate is through a phenomenon called quorum sensing. So microbes will send out communications, and they will likewise receive communications from other microbes that are within the biofilm. Now, part of this communication will be the appropriate time for that biofilm to begin the generation of the EPS, or the extracellular polymeric substance. This EPS will grow in the early creation of the biofilm. It'll protect the biofilm. Over time, if the conditions for the biofilm aren't ideal, the top layers of the biofilm will begin drying out and actually have the ability to slough off and begin floating off into the atmosphere. And so those microbes that leave the biofilm will leave to find another location to propagate and colonize a new biofilm elsewhere. And this is the mechanism for microbes both multiplying and then spreading as a result of biofilms. So what does this mean for air handling units? Well, biofilms thrive in cool, dark, and damp environments like those that we would find in an air handling unit. Air handling units are known amplification sites for biofilm, and multiple areas in the air handling unit are problematic, including the cooling coil, the condensate pan, in the wet, aging, saturated fiberglass insulation inside air handling units, as well on any surface that remains moist. What we're going to focus on today, though, is the cooling coil itself. Okay, so one of the characteristics of a biofilm is that they thrive on surface area. So the more surface area that exists, the more they'll thrive and the more they'll grow. This makes a cooling coil an excellent location for the growth of a biofilm. A standard 20,000 CFM cooling coil, which would be about 8 feet wide by 5 feet tall, has a 40 square foot projected area, but has just shy of 10,000 square feet of surface area, given the fact that you have 8 to 10 fins per linear inch on the coil. So this makes biofilms a perfect place to grow. Now, as biofilms grow on coils, they will disrupt the performance of that coil and cause it to perform at conditions below those design conditions for the coil. Now, what we're used to, it would be a typical coil cleaning process that would address a fouled coil. And that might consist of a hose, a pressure washer, perhaps a steam cleaner, and typically combined with some caustic or acidic chemical that facilitates the cleaning process. Now, these processes appear to work well. They actually do a good job of cleaning the outer 2 to 3 inches of the coil, but they fail to address the biofilm that grows deep within cooling coils that's hard to reach. And as a result, only equate to marginal improvements in performance of the coil. What we'll talk about today is what we like to call coil restoration, which is a more comprehensive means for cleaning the coil. It combines an innovative probiotic technology and a high-performance sanitization process that will clean coils right through to the center and completely eliminate biofilm from the coil. So how does coil restoration work? Well, there are 3 primary elements that are responsible for the success of coil restoration, and the first is the chemistry. And as I mentioned, we use an eco-friendly probiotic for the chemistry. Probiotics produce enzyme containing biosurfactants that will attack and break down biofilm on coil surfaces. The second element is heat. And the coil restoration process utilizes superheated water, which provides a combination of steam and high temperature water steam at 280 degrees Fahrenheit. That steam, that high temperature, allows us to emulsify and loosen the stubborn biofilm from deep within the coolant coil. And the third element is pressure. Coil restoration utilizes hot water at 1500 psi, which gives the ability to penetrate deep within coils and to completely remove that biofilm that's already been loosened by both the probiotic and by the emulsification process of the steam. Also part of the process is a reapplication of the probiotic after the coil restoration process is done to provide some ongoing biofilm blocking action for the coil. Now, the correct combination is all three of these elements, and so we're looking really to target at where these three elements intersect. That's really the point where we see the maximum end result performance of the coil. So with that, I'm going to show you a brief video that explains the coil restoration process. In this process, we would first apply a foamed probiotic agent both on the upstream and downstream face of the coil. This is applied so that we can get deep penetration of the probiotic into the coil, and it's left to reside for up to 4 to 8 hours to give time for that the probiotic to work on the biofilm. The second step is the application of superheated water, which is done also from the upstream and downstream side of the coil, and is very effective, as you can see here in the video, at stripping off the biofilm that's collected over time on the coil, biofilm that's typically very difficult to remove. So as I mentioned, this is done both on the upstream and downstream side. Likewise, there is a technician that is conducting the application of the superheated water. There's a second technician on the other side of the coil that's looking for the steam passing through the coil, and in doing that, looking for obstructions that might still exist in the coil so that we know what areas of the coil need to be focused on. This process is completed until we see a clear distribution of steam coming through the coil. As you see in the video here, we're looking for those defined fingers coming through without obstruction. Once that's done, there's a reapplication process of the probiotic agent. So what is the difference between coil restoration and typical coil cleaning? Well, the first thing, in a conventional coil cleaning process, you're utilizing either a water hose, a pressure washer, or a steam cleaner, which fail to both penetrate and clean deep within coolant coils. With pressure washer, there's often an issue where the pressure is too great, where it damages the fragile matrix of the coil. In the case of coil restoration, we're utilizing superheated water at 1500 psi, which provides just the right combination of heat and pressure to clean deep within the coolant coil. Another difference is that conventional coil cleaning typically utilizes environmentally toxic chemicals that have strong odors and contain VOCs. The coil restoration process utilizes an eco-friendly probiotic technology, which is GRAS listed. GRAS meaning generally recognized as safe as a food additive. So it is actually very safe to utilize in this application. And the probiotic is both odorless and free of VOCs. A conventional coil cleaning process uses chemicals that are often corrosive towards metals. And the use of them actually limit the overall service life of that coolant coil. The coil restoration process uses a probiotic that's pH neutral and completely inert to the metal of coolant coils. And finally, the conventional coil cleaning process fails to adequately address concerns of indoor air quality by virtue of the fact that they fail to address biofilm that's deep within coils. whereas the coil restoration process cleans clear throughout the coil, eliminating all biofilm through the coil and significantly impacting the indoor air quality as a result of the process. So now that we're on the topic of indoor air quality, I'd like to talk about a methodology for determining the microbial loading on a coil. We utilize a process called ATP testing. And ATP stands for adenosine triphosphate. And this is a test method that allows us to quantifiably measure the total microbial loading on a surface. The way an ATP tester works, ATP is a substance that actually exists in all living matter. And the ATP test itself measures or quantifies the amount of ATP that exists in that sample and provides a direct correlation to how much microbial activity is on that surface. ATP testing is conducted on site. One of the huge advantages of it is that it can be conducted within a 5-minute time frame. So it can be conducted and you could use it as feedback if additional cleaning of a surface is required. And the ATP testing is conducted both before and after the coil restoration process, which allows us to quantifiably determine the actual reduction in microbial loading on that surface as a result of the coil cleaning or coil restoration process. So a little bit more about ATP testing. ATP testing is reported in what's called RLUs, or relative light units. And it's actually a determination of the brightness of the sample when it's exposed to a chemical that activates the ATP. Now, RLUs are similar to, but should not be confused with colony forming units, which is the metric from a culture test conducted on a sample. And biofilm formation is directly related to the amount of microbial activity. And so the ATP testing gives us a direct correlation to the amount of biofilm formation that's on a coil. So we've put this chart together to give an indication of what a reading means. A reading of 0 to 10 RLUs typically would indicate no biofilm formation whatsoever. Up to a reading of 1,000 or more RLUs would indicate a full biofilm contamination of a surface. So with that, I'm going to move on to what we call tube restoration, where we previously talked about what we called coil restoration, which is addressing the air side of the coil. Tube restoration now addresses the tube side, or the water side of the coil, the interior of the copper tubes. Now, much in the same way we would see biofilm formation forming on the fins of a coil, we also see biofilm forming on the interior of tubes as well, in addition to mineral scale and debris that collects inside coolant coils. The result of this, as you see here, is the formation of scaling based on this scope done from the interior of a coil. Likewise, debris that collects inside the coil. And as you see in the video here, we see biofilm growing on the interior surface of the tube. The turquoise area you see are actually areas of corrosion, what we call mic, or microbial-induced corrosion. Now, the impact of these poorly maintained tubes is a reduction in performance of this coolant coil, both due to the reduced flow of chilled water and through the blocked heat transfer through the tube itself. Now, the process for tube restoration utilizes a unique patent-pending process that utilizes an eco-friendly probiotic agent. that's injected on the interior of the coil tubes. So in the process, the coils are filled with a foam probiotic agent. That probiotic agent will break down the biofilm that's building up on the interior surface of the tubes and help to recapture lost heat transfer efficiency. This dense probiotic foam is then pushed out of the coil. And the removal of the biofilm impedes future microbial-induced corrosion from occurring inside these coils. So for a quick look at this process, we'd start off with a standard cooling coil. We'd begin by closing off the gate valves, both upstream and downstream of the coil. By way of tie-ins to the coil, we would then connect a hose on the upstream and downstream side. And we would push in a foamed probiotic agent at approximately 60 psi. We would let that probiotic agent reside inside the coil for a couple hours, and then we would then begin to push it out. And we would continue pushing that foam probiotic out until we see that all of the debris and scale and biofilm have been removed. From there, we would go ahead and we would flush through clean water through the coil, and then we'd follow it up by reclosing the gate valves. Okay. So now we're going to move on to a different topic. We're going to discuss energy savings, and we'll discuss how energy savings can be derived from coil and tube restoration. We'll begin with a schematic of a typical air handling unit. And with this, we'll describe the areas of energy consumption that exist within this process. So the process begins with the blower that draws warm, unconditioned air into the coil. The coil then removes the heat from the air, and that heat is then removed from the coil via the chilled water system. From there, we have a uniform distribution of cooled, conditioned air coming off the coil, which then enters the blower and back into the building. Now, there are two areas of energy consumption in this process. The first is the blower itself, which operates at a predefined fan speed that allows us to provide an appropriate amount of cooled air, conditioned air to the space. And the second area of energy consumption is within the coil itself, the chilled water. It's the chiller itself, which is providing a predetermined flow of chilled water to the coil to provide appropriate cooling to the air. Now, where do things go wrong in this process? Well, the first thing is that poorly maintained coils will colonize and grow biofilm throughout the coil. And this slowly but surely reduces the amount of space or clearance in between each coil fin. This is made worse by the collection of debris and biofilm in certain areas, which begin to form complete blockages in the coil that greatly restrict airflow. So what we see now is as warm air enters the coil, we have areas of greatly reduced airspeed on the conditioned air coming out, and other areas of elevated fan speed or elevated airspeed to compensate for the reduced airflow of this cooling coil. The net effect of this is that the blower now needs to work even harder to compensate for the reduction in airflow across that coil. Another area where things go wrong and where an issue is created is in the fact that as warm air enters the coil loses its ability to properly transfer heat to the chilled water, or the biofilm itself actually prevents heat transfer. This is now even worse in areas of blockage on the coil, where it's completely blocking heat transfer into the coil. Okay, and the effect of that is conditioned air coming off the coil that is not at the decreased temperature that's required for the design of the coil. The net effect of this is that more chilled water is required to be served to the cooling coil to provide the appropriate cooling that will allow for the appropriate amount of conditioned air to enter the space. So to summarize that, where are the opportunities for energy savings? The first opportunity is in our ability to reduce fan energy consumption, and we do that through improved airflow. This equates to reduced fan speed with variable frequency drives. And what's important to know is that there's a cubic relationship between fan speed and energy consumption. So as little as a 10% reduction in fan speed as a result of coil restoration would equate to a 27% reduction in energy consumption for that blower. The second area for energy savings is in reduced pump energy consumption. And this equates to an increase in cooling capacity. Now within the coil, airflow, water flow, and thermal conductivity of the coil all work together in a very interactive way. And our ability to improve each of those have a tremendous impact on the cooling capacity or the efficiency of that coil. We see that improved cooling capacity decreases the requirement for chilled water or decreases the load on the chiller plant. And once again, we see that same cubic relationship now between the chilled water flow and the pump energy consumption. That would be the pump for the chiller. And as little as a 10% reduction in the flow of chilled water equates to a 27% reduction in the energy consumption of the pump. Okay, now how do we know this is true? How do we know that there truly is energy savings as a result of coil cleaning or coil restoration? Well, we know that because ASHRAE tells us it's true. Okay, a study was conducted by ASHRAE back in 2006. In this study, they utilized a conventional coil cleaning process and actually evaluated what the expecting energy savings would be as a result. And here was the data from ASHRAE. So in this study, they actually looked at 4 separate large air handling units that total 202 tons of cooling in a New York City high-rise. They utilized a traditional coil cleaning process, which utilized a pressure washer and caustic cleaning solution. The result of that process was an increase in airflow from 53,000 CFM up to 61,000 CFM post-test, which equates to a 14% improvement in airflow. So if you recall earlier, we talked about the fact that just a 10% reduction in the required fan speed equated to a 27% reduction in energy consumption. Now, the second thing they looked at was cooling capacity, and they measured a cooling capacity of the coils of 121 tons in pre-test and 140 tons in the post-test. This equates to a 16% improvement in cooling capacity of the coil, which would have a significant impact on the energy consumption as it relates to the power required to pump chilled water through the coil. Now, what ASHRAE tells us as a result of these improvements from before to after the conducting coil cleaning was that there'd be a 10 to 15% improvement in energy savings on an annual basis based on this coil cleaning process. Now, what we did, we really wanted to test this data ourselves, utilizing now our coil restoration and tube restoration process. We wanted to see what the difference would be in our ability to generate energy savings as a result of the coil restoration and tube restoration process. So in our case study, we looked at a single 50,000 CFM air handling unit up in New York State. We instrumented this air handling unit looking at 9 different parameters. It included a water flow, water temperature, air temperature, and air humidity for the incoming and outgoing air, and likewise air velocity measured with the traverse readings. We conducted both coil restoration and tube restoration on this air handling unit. And the M&V study collected both pre-test and post-test readings under highly controlled condition to ensure accuracy of our results. The results that we found were that for airflow, we saw an increase from 46,000 CFM pre-test to 53,000 CFM post-test, which equated to a 14% improvement in airflow. Now, it's worth noting that with this air handling unit, it actually started out being rather clean. In fact, we suspected that it was clean probably 6 months prior to us conducting this analysis. And so with the 14% improvement, we were very happy with that, especially seeing how it actually matched the exact improvement that ASHRAE saw in their study. As it related to cooling capacity, we saw an improvement from 275 or 276 tons of cooling to 377 tons of cooling post-test, which equated to a 37% improvement in cooling capacity. Now, this far exceeds what was experienced from the ASHRAE test, which I believe was 13%. We believe much of it, this is due to the use of our probiotic and our coil restoration process, but also due to the tube restoration process, which was also conducted. We also, in the process, conducted ATP testing, as we talked about before, and we found an ATP reading on the face of the coil of 5,732 pre-test, and we measured an ATP reading of 0 post-test. The 5,000 reading obviously being a substantial contamination of biofilm prior to us starting, and afterwards the reading of 0 would be 0 biofilm or 0 microbial activity post-test or after the coil restoration was conducted. Now, with this, we're still working with the customer to determine a more precise energy savings, but we know that the energy savings would be far in excess of the 10 to 15% range that was determined by ASHRAE for the study that they conducted. So in summary, looking at the benefits of coil and tube restoration, the first benefit we see is the ability to substantially unlock the cooling capacity of the coil or improve the efficiency of that coil. We've noted from various tests that we've conducted that we've seen cooling capacity increases by as much as 50%. This would in turn lower the demand of chilled water to that coil and drive significant energy savings by lowering the load on the pump that drives the chiller in the process. We've also noted our ability to renew airflow performance or to significantly reduce the resistance of flow or resistance of air through the coil, which we've measured to be upwards of 50% on the field trials that we've done. This lowers the bands on the blower and equates to significant energy savings overall. As a third benefit, we note the improvement in indoor air quality, or our ability to clean coils at a microscopic level, and eliminating biofilms that contain pathogens such as Stachybotrys, Staph, Legionella, or COVID-19. And lastly, we note our ability to extend the serviceable life of cooling coils. So this can prolong the life of a cooling coil, delay the high capital expense of replacing cooling coils, or perhaps even as a result requiring the replacement of a complete air handling unit. So with that, concludes the presentation. I'd like to open it up at this point to any questions that you might have.
Thanks, Mike. We actually do have a few questions. By all means, if anybody has any questions, please feel free to add them. But let's start with one question. Is this all done while the coil is in place, or do you remove it?
I'm sorry, my mute was on. This is all done with the coil in place. Generally, the process requires as much as 4 to 6 hours for smaller air handling units that are perhaps 20,000 CFM and smaller, and up to 8 hours for larger coils, ranging up to 40, 50,000 CFM. Everything, though, is done with the coil in place. All we're doing is shutting down the air handling unit, and we're isolating that unit to prevent any potential odors or process air from escaping and being detectable by the occupants of a building.
Great. Next question. Is the foam just for coils or a whole chilled system?
Great question. At this point, we've only utilized the foam on coils, both on the air side and water side of coils. We've also utilized the foam for addressing, in some cases, cooling towers, which is a service that we're actually launching this year. And there certainly is the possibility to utilize the foam probiotic to address chillers and address other parts of the cooling process, the cooling system. We've yet to do that, but the application is certainly there to do that as well.
Okay. And how long can one expect the coil treatment to last? And will you need to do this on some type of periodic preventative maintenance schedule? Got a great question.
Excellent question. This is really highly dependent, and it depends on the fouling rate of the cooling coil. This could depend on geographic location. This could even depend on the specific location within a hospital. If it's a fresh air handling unit, or if it's utilizing return air. I'd say generally speaking, the process should be conducted anywhere between annually and every 2 to 3 years. Annually for when you're dealing with higher fouling rates, or perhaps air handling units that are highly sensitive to fouling. And we have other customers that do it on a 2-year or 3-year basis. What we see most often, though, is people who do it annually.
Okay, great. We're getting lots of questions. If for some reason your question is not answered, just due to time constraints, we will definitely get back to you by email directly. But another question, Mike, does it improve the, quote, musky smell complaint?
It does. There's a phenomenon that's called, usually called stinky sock syndrome or smelly sock syndrome. And that's actually related to a specific microbe that grows on coils. And the probiotic process does do a good job of addressing that issue. And so it does address odors. We've had cases where it's been bad enough that it has required coils to be cleaned more than once a year, or even in some cases just sprayed down with a probiotic periodically to address that odor issue. But it does, in fact, address the issue, and we've been called in cases where this issue exists, and we've been able to address it.
All right. And do we capture the foam and debris from inside the tubes, or do we send it to the drain? The question was specifically in reference to drained water that tends to be monitored by the city water department.
Excellent question. We do, in fact, collect that water before we do anything with it. And I think you probably even noticed in the video where we collect it in a 55-gallon drum. Now, generally speaking, that water that we collect that's filled with a probiotic and biofilm, that's actually an environmentally positive substance, in that it actually would improve the quality of your sewer system. And so there's no issue whatsoever with putting it down the drain. We would typically put it down the drain. If a customer requested that we did something else with it, we can certainly do that as well.
Okay. Common question, what is the cost for the restoration process?
You know, I'm going to kind of refrain from answering that too specifically because it's highly dependent on the size of the air handling unit, the quality of the air handling units, quantity of the air handling units that are being conducted. So I say, you know, I'll talk in general terms. In general terms, you know, for air handlers that are smaller than 20,000 CFM, you would be looking at, you know, for the complete process, you know, well south of $3,000 to $4,000 per air handler. For air handlers that are much larger in the 40 to 60,000 CFM range, you know, you'd be looking above that number. And so, but to give anything more specific, we would really want to come in and have a look at those air handlers for you and give you a precise cost.
Great. What do you do in the event that the isolation valves do not hold? That's an interesting one. I don't recall these stuff.
Yeah, that's a really good question, and it's something that we deal with all the time. You know, we would conduct an inspection of the air handling unit prior to doing any work on it. If we were to find that either the tie-ins or the shutoff valves aren't working properly, we would ask the customer to repair them prior to proceeding with the tube restoration process. It doesn't matter, obviously, for the coil restoration process, but for tube restoration, it does. And so we do run into this at times. And in fact, what we'll do is we'll conduct a survey of all the air handling units for a customer. They would then proactively go ahead. They would address any concerns, and we would come in and conduct tube restoration on all of the air handlers at once.
Okay, great. We've had a couple of questions specific to the brand of probiotic foam, the brand of probiotics that we're using. I'm sure you'd want to.
Sure. You know, that's an aspect that I really can't get into, and it's patent protected. And so, you know, I can tell you that the probiotic does contain a strain of a variety of probiotics, and so that help its effectiveness. You know, probiotics are so effective because they essentially produce enzymes. So whereas, you know, other processes that out there claim to use enzymes, the use of probiotics is actually like putting an enzyme factory on your coil that's manufacturing probiotics and continuing to do so over time, rather than using an enzyme that gets used up in the process and no longer becomes effective. So, you know, the use of probiotics is key to our patent, and so I really can't talk more about which specific probiotics we're using.
Okay, great. Well, it looks like we've got about 30 seconds left here. I'm not sure how that all works. Billy, is there anything you'd like to any questions that weren't covered, by the way? We will go through every single one of them and reach out to you directly to answer those questions. Billy, did you want to take it from here? Thank you, everybody.
Yes. I just want to thank our presenters, both Mike and Christina, for your time today. And as always, thank you so much for the people who took time out of their busy workday to join us. I thank you. Be safe, stay healthy, and until next time, have a great afternoon. Bye-bye now.